Hello everybody, welcome to the Physics and Astronomy track. My name is Gwen Period-Mojo and I'll be the chair for this session. So Sanjiban, the floor is yours.
Okay, thank you. Thanks for joining us here today. I'm Sanjiban and I'm a doctoral student at CERN, affiliated to the University of Manchester, where I'm researching efficient machine learning inference through heterogeneous architectures, specifically for the upcoming upgrades at CERN, which we are going to see what are today. So you probably have heard about CERN, which is like the largest scientific facility in the world, where the World Wide Web was invented and the Higgs field was discovered. One helps us to stay connected. One gives us mass. So it's like this large scientific facility where many people are working to understand what we are made of, how we are made of, and it popularly houses the Large Hadron Collider, which is like a very large ring across the Franco-Swiss border, having a circumference of like 27 kilometers. And there are 4 major experiments: the ATLAS, CMS, LHCb, and ALICE. ATLAS and CMS are more general purpose experiments, whereas ALICE and LHCb are more specific for a particular use case. And people there are trying to understand what exactly happened, like just right after the Big Bang, by accelerating particles into very high speeds which are close to the speed of light, and they collide those particles, thereby understanding what might have happened just after the Big Bang, and then understanding what are the properties of matter, what we are actually made of, and what are our behaviors, and etc. Now, in all those analyses, we use artificial intelligence and machine learning in various purposes, from using classification models to actually identify events which are interesting, which can be used for further analysis. We use anomaly detection models to actually see if there is any particle or any event which does not follows what our current understanding is, thereby indicating there might be something which can be interesting to further research on. And we also use like generative models for simulations to actually see if what we are getting from the experimental data follows our theoretical predictions or not. And in all those analyses, one of the biggest challenges that we face is the data volume that we generate. So just to give you like a comparison, this is a figure from 2023 where we can see that like the AWS had about 500 exabytes of data in total. But at CERN, the collision data that was generated was about 40,000 exabytes just in a year. So that's like a huge amount of data that is generated, which is both technologically and logistically very challenging to store and process. So instead of following the traditional paradigm, we follow a different paradigm in which we do not actually store all of the data that we are producing for further analysis. Instead, we do a real-time data analysis where we analyze the data as soon as it is collected, and to check if it is something interesting to actually store. If it is not, we just reject all of that data. And we do so by using these systems called triggers. Triggers are systems that helps us to analyze those data in a real-time manner. So just to give an example, the detectors at CERN produces data, like the collision data, 40 million times every second. So it's like a frequency of 40 megahertz. And about like 60 terabytes per second of data is passed through triggers. And the first trigger is like responsible for reducing the data rate to 100 kilohertz by rejecting like 99.75% of all the data. And the difficult part is it has only about 5 microseconds to make that particular decision. And then it goes to the high-level triggers, which again like reduces the data rate to 1 kilohertz, and it does so by rejecting 99% of the data. And it also has like about 0.5 seconds to make that decision. Now, the level 1 triggers are mostly hardware-based triggers. It's mostly comprises of FPGAs or ASICs, while the high-level triggers are more software-based, running on like CPUs or GPUs. Having both of them can have machine learning models and also like traditional algorithms running to actually decide if a particular event is interesting. And only then the data are stored in offline analysis, which is like only 0.0025% of the actual data which was produced. So it's very important for these triggers to not only analyze and like process this amount of data in a very high rate, but also to do it correctly, because if the data is rejected, it is lost forever, and we might lose a very interesting data which can actually help us to further research something. And the numbers that I just showed are like the current numbers that we are having at the LHC, but CERN is also preparing for like the next phase of the Large Hadron Collider, which CERN says as the HLHC, the high luminosity phase of the Large Hadron Collider, where the data rates are going to further increase, and it will be very difficult for the current computing infrastructures to make up with that increased data generation rates. So I'm a part of this new project called the Next Gen Triggers project at CERN, where we're working on new computing technologies and systems that can help us handle that data acquisition and processing in the next phase of the Large Hadron Collider. So as I said, machine learning is applied across several of the experiments and analysis at CERN. And while the first four, the stages of machine learning, from studying a case and to training a model, then testing and evaluating it, can be done in offline, but the inference stage becomes difficult because of the tremendously high data rate. So we need smarter models, we need smarter approaches to actually infer those machine learning models in a very efficient manner, and with the limited computing resources and the limited time. So two of the major experiments at CERN, like the ATLAS and the CMS experiment, they have their own frameworks called Athena and CMSSW, which are proper software frameworks which are used for data analysis, for data storage, and they have the inference pipelines for machine learning models, and both in an inference as a service model and both for direct inference. In inference as a service, they use NVIDIA Triton server, and for direct inference, they mostly use ONNX runtime. For inference as a service, Atlas and CMS has their approaches, which are quite similar. They're called as Athena Triton and Sonic. Both of them mostly work in a similar fashion, in which the data processing workflows, that is the clients, they offload the computationally intensive steps into co-processors, like remote server co-processors. So basically the idea is that we cannot just rely on CPUs for actually inferring all the machine learning models on considering the data that we have. So we need to use co-processors, that is FPGAs or GPUs or ASICs, to actually offload the inference stages, the inference steps, and into them. So, and even for the direct inference, we use they use ONNX runtime, and so ONNX, which is the Open Neural Network Exchange, is a standard, is a format which is used to represent machine learning models in a graph format, in which there are nodes which represent the actual mathematical operations through which the tensors, like the input tensors, flows, and at the end we get the resultant output tensors of the machine learning model. The ONNX runtime is a high-performance, interoperable inference engine that can help us infer machine learning models through the ONNX format. It was developed by Microsoft. It's open-sourced, and it is cross-platform. So this is currently used in several of the direct inference approaches at CERN, but we still face some challenges using ONNX runtime, mainly because ONNX runtime does have some external dependencies to handle, and at CERN, it is difficult to handle such external dependencies, and we also need more fine-grained user controls than what ONNX runtime provides us. And there are also certain machine learning operations which are not quite supported by ONNX runtime, specifically the graph neural networks. CERN uses a variety of graph neural networks for its analysis, which are not quite supported for inference in ONNX runtime. And it's not quite easy to actually just convert any machine learning model to ONNX. And also, like in a previous research, it was found out that ONNX runtime inference values may vary in the last digits for different runs. So this challenge in the precision of the resultant output from ONNX runtime also becomes like a difficulty in using ONNX runtime in the inference pipelines. And for that reason, we are at CERN, we are working on this new tool called SOFI. So SOFI stands for System for Optimized Fast Inference Code, EMIT. It's like a tool that can translate your trained machine learning model into standalone clean C++ code, which only depends on BLAS and nothing else. So it has these three components. Firstly, a parser that can translate a model which was trained in Keras, PyTorch, or Onyx, and then it converts it into Sophie's internal representation, which is also based on Onyx, and then it generates inference code from the generator, and it's just a C++ header file which you can just include in your project, and then you can call for inference. And right now it supports several of the Onyx operators like gem, ReLU, convolution, RNN. It also supports complex models like transformers or even graph neural networks. For its API, so Sophie has both a C++ and a Python API for and the model weights, and then we can call this infer function to run the inference for that machine learning model. We can also use this inference functionality within Python. So Sophie is integrated within the root data analysis framework, which is one of the popular frameworks used in high energy physics. So we can use the root cling interface and use the generated C++ header file through the Python interface as well. Now, so Sophie in functionality was really good because it is just plain C++. It has a very fine. It gives the users very fine user controls, and then it only depends on BLAS. So that all looks very good. But when we ran benchmarking against Onyx runtime, which is a comparable framework in our purpose, we found out that Sophie performed better for smaller models and single event evaluations in time and memory, but it took longer time and intensive memory in inference of very large models like ResNets or particle nets. Reason is Sophie did not have any optimization at that stage. So we started working on adding optimization mechanisms to reduce the memory usage and the inference latency. So we were adding several of the optimization methods like reusing memory or fusing multiple layers or few operators into one, and then broadcasting tensors more efficiently, then eliminating operators from the actual inference graph, etc. So one of the optimization method I would like to talk about is the memory reuse. So in any kind of machine learning model, what we have is it's like for example in this machine learning graph we have an input tensor which flows through the graph and is processed into with particular operators. So for example, the first gem in this case, it processes the input tensor and then it needs some memory to offload its output. So in this case, it offloads it into the intermediate tensor 1. And then that becomes the input to the next operator, that is gem 2 in this case. So in the initial case, what we used to do is we used to just allocate memory for all of the required intermediate tensors, which is quite inefficient because we can just reuse some of the memory. So for example, in the initial case, we can just allocate memory for the first and the second intermediate tensor here. But when the second gem is done processing the intermediate tensor 1, that memory block is free to reuse, right? So the intermediate tensor 3, instead of allocating memory all over again, it can just reuse that particular chunk of memory. And similarly, the same kind of memory reuse can be done in the graph. And one advantage that we get in Sophie is we are doing such allocations ahead of time because we know that how much memory all the model is going to take when any particular intermediate tensor is going to arrive. So we know that information beforehand. So what we basically do is allocate a big block of memory and we just use pointers, memory pointers, to move over that memory to find out which are the positions in that memory where a particular tensor can be stored during the runtime. So we're not doing any kind of memory allocations or deallocations during the actual inference runtime so as to avoid any I/O overheads, and that helped us to reduce the overall memory overheads. So when we ran benchmarking after this optimizations, so we found out there was a 50% reduction in the total memory overhead from what we had before, but we are still taking more memory for complex models. So this graph is you plotted on the particle net, which is like a graph neural network model by the CMS collaboration. And so we are still taking more memory than on-X runtime. So we are still working on researching further optimization methods that we can implement to reduce this memory overheads further. Now, this implementations on optimizing machine learning inference is also subjected for a future goal of high luminosity phase of the LHC. As I mentioned before, that we cannot just rely on CPU for executing all our machine learning inference models. We need to use GPUs and FPGAs. And one difficulty that comes on with such heterogeneous inference is the bottleneck where if our machine learning model is dependent on the actual architecture where we need to execute our inference. So instead of moving our data, our memory buffers to the CPU and then to actually execute the machine learning model, we need something through which we can just interface for interoperability. That is, doesn't matter what heterogeneous architecture we have or what kind of data buffers we have, we can still perform inference on the particular target architecture. Now we're trying to do that using abstract libraries like SYCL and Alpaca. So SYCL is a library by Intel, while Alpaca is a library, is an open source library being developed by the CMS collaboration and also the Helmholtz collaboration from Germany, which is like an abstract library which gives us data buffers that can be processed, that can be moved in varied architecture. So it's not hardware specific, it's hardware agnostic. So the same data buffers can be moved in both NVIDIA GPUs, in AMD GPUs. So the target is that right now the SOFI generates C++ code which uses like std vectors, like simple STL vectors for all the data arrays or like tensors. In the future, we would like to generate C++ code which will have this Alpaca buffers, and Alpaca buffers will help us to not be specific to a particular hardware architecture. Instead, it's during runtime where we decide which architecture we want to perform the inference actually. So the architecture should look like something like this, where we have a buffer accessor model, and the SOFI's generated code will instantiate buffers during the session instantiations, and we will accept buffers as inputs, will return buffers as outputs, and the info function that we'll have will be abstract. So it will not be specific to just CPUs or even NVIDIA GPUs. Instead, it will be having, because it will be having Alpaca buffers, it will be open-ended, and it will depend on like how the user wants to actually execute on a particular interface. So it's on the user who can basically specify that, okay, we want to run it on NVIDIA GPUs, on Intel GPUs during the runtime, and the code that we generate, it will automatically choose the BLAST methods or any particular functionality for the GPU or the target interface accordingly. So in the current status, we have a SYCL prototype that we have developed, which is under testing, and we also have an Alpaca prototype for NVIDIA CUDA, which we are currently testing on using GEM and ReLU operations. Right now we are particularly focused on this Alpaca prototype because CMS uses Alpaca in majorly of their heterogeneous architectures work. So we would like to produce C++ code having this Alpaca buffers so that it becomes easier for them to also integrate in their inference pipelines. So in the future, we plan to continue our research on adding further optimization methods to reduce the overall memory overheads and latencies for machine learning inference. We would like to extend the support for inference on heterogeneous architectures through Alpaca. And we'd also like to benchmark like the heterogeneous support with other frameworks like on-X GPU. And we would also like to add like interfaces to TensorRT and like ROCm. And there is another framework which is quite similar to what SOFI does. It's called AI Template. It's by Facebook. So we'd also like to experiment with it and see the comparisons that we have. And there are some other projects that I would like to mention that which are like my team is currently involved in working on. So it's like the first is HLS for ML. So that's like a library that can help us port deep learning models to FPGA. So basically, HLS4ML is like a library which can take your trained deep learning models and then convert it into high-level synthesis code, which can then be used for inference on FPGAs. And then we also have a project called Conifer, which does the same as HLS4ML, but for boosted decision trees. So although we have deep neural networks which perform really good and helps us to do our analysis in physics, but boosted decision trees are also one of the good alternatives that we have, which are comparable in accuracy but have a very low latency, so which are very helpful for the analysis. And we also have pQuant, which is a library for like model pruning and quantization. So the idea is that after a model is constructed in like Keras or PyTorch, we can call the pQuant functions for its training, for like quantization and pruning away training, and then that optimized model can then be executed in the GPUs or can be passed through HLS4ML for generating high-level synthesis code for AMD or Intel FPGAs or even SOFI. So I would start concluding my talk. So SOFI is within the root data analysis framework. So we would really welcome any contributions or any feedback on our project or our work. And I would like to thank the Eric and Wendy Smith Fund for Strategic Innovation, who are funding our project through the Next Gen Triggers project. And I'm also thankful to SkyPi's financial aid program for supporting my travel to present at this conference. And my personal thanks to my friend Shreya, who suggested me submitting a proposal for SkyPi. Also, check out her virtual poster on automating solar quark identification with Python. And yeah, I will finish my presentation. We can go on Q&A. Thank you.
Awesome. Thank you so much. We have a few questions in the chat here. First one, Matthew Fikert. For the LHC experiments, are the GPU resources centrally provisioned from CERN, or is it expected that each university or research institution provide GPU resources?
It kind of depends on what the use case is. Many of them are centrally provisioned at CERN, so like the GPUs stay within the CERN's like the data science labs, and some of them are like stays within the university. So it kind of depends on the use case.
Cool. And I have another question. In which formats are you storing the format weights in the inference codes?
So we store in two formats. We store in .dat, like so SOFI can generate an inference code and store the model weights in like a .dat, basically the binary format. We can also store in the .root format. So root format is like one of the compression formats by the root framework. So it's like popularly used within the physics research. We can also keep the model weights within the header file, like if the user wants, like if the weights are not that big, so it's actually better to keep the weights within the header file itself. So yeah.
I got two more questions. Do you support only static inference or also dynamic inference?
We do support dynamic inference. Basically, we try to figure out how much, like, what's the scale of like tensors that you will have while your during your inference pipeline, and using that you can actually like extend your tensors during the inference pipeline as and when required.
Then last question, also from Matthew Fikert. You mentioned that SOFI was able to generate standalone C++ header-only software.
Mm-hmm.
Standalone C++ header-only software. Is it itself standalone as a header-only library, or does it require root as well?
It depends on what you want as your inputs to the model. If you want your inputs like as std vectors, then it doesn't require root as a dependency. But if you want to pass like root's R data frame like inputs to the model, then it requires root for that. Otherwise, it just does not need root.
All right. There's no more questions, so let's thank the speaker one more time.
Thank you.